Hi there and welcome to this small presentation on capacitive reactance. Okay, let's have a look at our little circuit here. Let me quickly introduce all the equipment we've got here. We've got a little breadboard. There's a capacitor here where you can see the finger, and there's a resistor there, and you can where I hold the finger as well. We've got two multimeters. They're both set to read AC voltages. So we've got the one on the left is connected across a capacitor, so we can read the voltage across a capacitor, and the one on the right is connected across a resistor, so we can read the AC voltage dropped across a resistor. And then that thing here is an old signal generator. I haven't checked it out, so I'm not quite sure how precise it is, but we'll see during the demonstration how well it works. Okay, let's have a look at the circuit. We've got the circuit here on a piece of paper. It's a very simple circuit. This is our AC supply, so that's our signal generator, and we've got a resistor here, and we've got our multimeter connected across the resistor, and we've got our capacitor here, and we've got our multimeter also connected across the capacitor to measure the AC voltage, RMS AC voltage across the resistor and the capacitor. Okay, that's the circuit so far. What's reactance all about? You know, we all know Ohm's law, we all know what a resistance is all about, but then we've got this funny thing about reactance. And all reactance is that if we measure the resistance with a multimeter and we measure it in DC conditions, in direct current conditions, we get a reading. Yeah? So for example, we stick it across our resistor, and this particular resistor has got a resistance of 150 ohms, and we read 150 ohms. And we pretty much know that this resistor is going to behave the same way. It doesn't matter whether I put an alternating current through it or I put a direct current through it. The resistor will always have 150 ohms. Now, we've got coils and we've got capacitors. And something happens with our capacitors when I measure the resistance at DC conditions, and then something happens when I do the same thing and I try to work out the resistance, but I'm feeding an AC signal through the capacitor. And that is called reactance. So for example, if I take a capacitor and measure the resistance at DC conditions, I'll get something like infinite resistance, several megaohms. So it's really, really high. It's sky high. But then I place it into a circuit and I apply an alternating current. What I find is that suddenly the capacitor behaves like it's got some sort of dynamic resistance. So the higher the frequency goes, the lower the resistance with the capacitor. Now, we don't use the term resistance for that, we use the term reactance. Why do we use the term reactance? Because a capacitor and also a coil, but in opposite ways, they do react to an alternating current in changing their resistance. Yeah. Again, reactance is the symbol is X, and we measure it also in ohms, just the same as resistance, but the only difference is it varies with frequency. Okay, let's look at the formula here. So this is the formula. Xc is equal to 1 over 2 pi Fc. So 2 pi is 3.14, and then our frequency, again, whatever it may be, and then we've got our capacitance as well. In this instance, we've got a 1 microfarad capacitor, and we're looking for a target frequency of 1000 hertz. And at 1000 hertz, my capacitor will have a reactance, to make sure, a capacitive reactance of 159 ohms. So there'll be a reactance, Xc, of 159 ohms. So in theory, having a 150 ohm resistor here and having a capacitor that at 1 kilohertz should have a reactance of 159 ohms, we should find the same voltage drop on this multimeter as well as on that multimeter. And we're going to test it out now. Okay, at the moment we are near enough DC conditions. Let's have a look. The signal generator is set to 10 hertz. The multiplier is set to 1, so it's about 10 hertz. We're going to go down a little bit. And what you can see is, I'm now at about 4 hertz or something. We see that on one side we've got a voltage of 7.7 volts. It sort of fluctuates a bit. I think it's struggling, the meter is struggling to deal with such low frequencies in AC mode. And here we've got 2 millivolts. So what we can say is, the capacitor has got a very, very high resistance. Yeah? So at least 1,000 times higher, it's about 2,000–3,000 times higher than our 150 ohm resistor to drop most of the voltage and only allow the resistor to drop about 2 millivolts. Always remember, when you use Ohm's law, big resistances in a circuit drop big voltages, small resistances in a circuit drop small voltages. And so this resistor at the moment drops a very small voltage, and we know the resistance is 150 ohms. That means the reactance of this capacitor must be several thousand times higher. So it's got a very, very high resistance. So we are at the moment somewhere in the kilo ohm range. We could sit down and sort of do the exact calculations. But again, this is just about showing you a principle. And the principle is that as we increase the frequency, the reactance or the resistance will go down with our capacitor, the apparent resistance. And again, we know our resistor doesn't change. It's going to be 150 ohms all the time. Doesn't matter what signal we are feeding through it. Okay, we're going to go to a multiplier factor of 1. So we've got 10 hertz exactly. We get about 50 millivolts dropped by our resistance. And we get about 7 volts dropped by our capacitor. Let's sort of try and see whether we can get a factor of 100. So when we go to about, again, it's a signal generator. I'm not sure how precise it is with the frequency. But when we go to about 12 hertz, at 12 hertz we've got a factor of about 100. So that means times 10 would be 1,500 ohms. On that one, times 100 would be 1,500, 15,000 ohms. So we've got about 15K now in our reactance, in our capacitor, and we've got 150 ohms in our resistor, which again doesn't change, but we can sort of just therefore compare one with the other. I hope I got those figures right. I'm just doing it out of the top of my head. Anyway, we're going to carry on. We'll go up to let's have a look. We go up to about 100 hertz. Yeah? So we are now at 100 hertz. Let's see what's happening at 100 hertz. And it's interesting as well. We have increased the frequency by a factor of 10. And again, the difference now between both voltages is only times 10. So we've got 150 ohms here. And the reactance, when we look, we've got 7.28 volts dropped across our capacitor. And we've got 700 millivolts dropped across our resistor. So when we look at the difference now, it's a factor of 10. So we know that that one is 150 ohms. So therefore, the reactance across our capacitor must be 1.5 kilo ohms. Yeah, so 1,500 ohms. So we've gone down from about 15,000 ohms to about 1,500 ohms by just increasing the frequency from about 10 hertz or 12 hertz to 100 hertz. Yeah. So can you see what's happening here with our capacitor? Yeah? It's responding to frequency. Frequency goes up, resistance goes down. That's what we have established here so far, using just basic concepts of Ohm's law. Okay, shall we go a little bit higher? Let's double it up, go to 200 hertz, see what it does. Yeah? And at 200 hertz, we suddenly see we've got 5 volts across our capacitor, and we have got a little bit more than 1 volt across our resistor. And so we can see that suddenly it's only 5 times as high. So it's about maybe 700, 750 ohms across our capacitor. That's a reactance of our capacitor, and dropping about 5 volts at 750 ohms or something. Round about there, roughly. So we are not too picky about the figures. It's all about the concept of what's happening, when we measure, when we expose our capacitor to frequency. And what you can see now is reactance, the resistance, the apparent resistance drops down, goes right down. Okay, I'm going to sort of go back up, and we're now going to go to 1 kilohertz. Yeah. And when we go at 1 kilohertz, we can see it's almost the same. We've got 1.2 volts across our capacitor, and we've got 1.5 volts across our resistor. So we know, I don't know how precise the signal generator is. It might be slightly out with the frequency, but we are about there. It's about half and half. And that's, when I look at this formula, that's what we try to figure out. At 1 kilohertz, the capacitor should have 159 ohms, and we've got 150 ohm resistor, so it should be about half and half. And we are almost there. Let me just get it to half and half and see what frequency comes up. Ohm's law doesn't lie, signal generators do. So we are now at about 800 hertz according to the signal generator, and we've now got sort of a ratio of half and half. So both the capacitor has got the same reactance as the resistor has got resistance. Yeah. So it should be about 150 ohms now. And again, we've calculated it should be at about 1 kilohertz. Signal generator tells us it's about 800 hertz, but these are old boxes and they sometimes go a little bit loopy, so they might not just be spot on. Right, so we've done that. Okay, what next? Let's go a little bit crazy and go up to 2 kilohertz, see what happens. Yeah. And what we find is we've got gone a little bit above, I think. And my little meter switches off again. Let's switch it back on again. Okay, so we've got about half the voltage now. So that means we've got about 75 ohms across our capacitor. And we've got still 150 ohms across our resistor. So that's what we can tell from this voltage distribution, looking at Ohm's law. So it's dropping less and less voltage, which means that the resistance or reactance of our capacitor is going down. Always remember, big resistances drop big voltages. Small resistances drop small voltages. So the resistance or the reactance of that capacitor, of that thing here, is getting down and down as we increase the frequency. So we are now at about 2 kilohertz. It's 1.8. I'm going to go a little bit higher. And you can see it just goes down. It goes down further. Okay, let's go really, really crazy and go to 10 kilohertz. Yeah? Go to 10 kilohertz and see what it does now. The signal generator doesn't spit out as much juice. Yeah? The voltage, the signal has gone right down. But again, we are just looking at ratios, so it doesn't really matter. We have got just about a volt across our resistor. But when I look at our capacitor, it's only dropping about 40 millivolts. So we've got about almost a volt, and then we've got 40 millivolts. So the ratio has gone the other way around now. So it's about, is it 10? 10 would be 400. It's about 20. Yeah. So 150 divided by 10 is 15. Divided by 20 would be 7.5. So my capacitor has now got a reactance of 7.5 ohms, approximately, about there. So we've got about 7.5 ohms. And that's quite low. It's almost like a piece of wire now. Before, when we started off, it was almost like an insulator where it didn't drop, where it dropped the complete voltage, meaning that the resistance was so high that my resistor wasn't hardly dropping anything, but the capacitor was dropping it all. Okay, we're going to go really, really crazy, and we're going to go up to about 20 kilohertz. And again, when I look at the ratio now, we've got about half a volt across our resistor, and we've only got about 3 millivolts across our capacitor. Yeah, so you can see, what's happening here is going more and more extreme. One thing I have to say though is I'm not quite sure what these meters are configured. They're normally configured to operate at 50 hertz. So going up to about 20 kilohertz is kind of pushing it a little bit with these meters. Also, the signal generator is not putting out the full power. What I should be doing is using a scope, but it gets a bit messy, sort of reading all the, interpreting all the traces on a scope. And here we've just got numbers, and it's a little bit easier to trace through. But it doesn't really matter, whether the way the meter works, and we are losing a little bit of our signal because the way the meter is set up. Or both digital meters are set up, but the main thing is we are looking for the ratio of the voltage drops between our resistor and our capacitor. And one thing we have proven is that we increase the frequency, so F goes up, reactance, XC goes down, and reactance is something which at DC conditions has got either very high resistance or like a coil, a very low resistance, that they change the resistance when we apply AC. And we call this reactance because it's reacting to AC. Okay, thank you very much for listening to and watching this video. Hope this helped a little bit to clarify what reactance is. And that's all. Have a great day.